Welcome all of you. In the last class, we did discuss extensively the analysis of the carbon-13 NMR spectra. I took lot of examples where we could analyze the spectrum based on the chemical shift and also coupling information. And I wanted to show you the spectrum of carbon-13 coupled with the heteronuclei, abundant spin like phosphorus, fluorine, etc. And we could clearly see the multiplicity pattern when in several of the examples we took. CF3 group coupled to carbon will be as a quadrate, and then we have a 2-bond coupling, 3-bond coupling like that, and we were able to assign most of the things. So, when you are directly detecting the carbon, the question of dilute spin does not arise at all. That is what I have been telling you. So, in the spectrum, in the analysis of the spectrum directly gives you coupling of carbon-13 with abundant spins. What happens if there are abundant spins in the molecule, dilute spins in the molecule apart from abundant spins? For example, selenium, silicon like that. But you are detecting carbon, that itself is a dilute spin. But when you are detecting, do not worry about that dilute spin. Then other dilute spin can appear as a satellite for this. This is a very interesting example. We took this as an example with the tin, and I took the example and showed how the satellites of the tin gets reflected, especially tin 117 and 11N, two tins, two isotopes give rise to satellites with two different coupling strengths, and the intensity was approximately equal to their abundance of 7 or 8%. Both of them are nearly equal to 7.8 and 8.4 of that order of abundance. So, intensity was also agreeing. You are able to get the heteronuclear coupling from the satellite spectrum. That is fine. And when we have a complex multiplicity pattern, identification of the carbon even after decoupling protons is a difficult job. Even though you simplify the spectrum by decoupling, but still, how do you assign which carbon is which, like whether the CH3 carbon, CH2 carbon, CH carbon or quaternary carbon? How do you make the assignment? Of course, retaining the decoupling. We have to decouple, break the coupling and still assign. Otherwise, if there is a coupling, we can still know CH3 is a quadrat, CH2 is a triplet like that. In spite of complexity, somehow we can work with it with a enormous difficulty, we can identify at least to some extent. But here decoupling is there. Removing carbon proton coupling, still we have to assign the carbons based on the attachment to different carbons. How many number of carbons it is attached to CH3, CH2, CH like that. How do we do that? For that I said depth experiment. Depth is a simple pulse sequence where the proton carbon-13 has 2 pulses on the carbon-13 channel, proton has 3 pulses. The last pulse on the proton is a flip angle pulse. I said that flip angle of the pulse, we can do 3 experiments, 45, 90 and 135. When it is depth 90, only CHS will be there, all positive. Depth 135, CH and CH3s are positive, CH2s are negative. In the conventional spectrum, all carbons will be present. So, combination of all these things you can see, identify which carbon is which. Very fairly it is easy to do that. And I showed the example in a complex molecule like cholesterol, how depth experiment helps us in identifying the carbons based on the number of protons attached to it. That is what we did. Okay, going further, I also said using carbon-13 NMR we can even make the structural assignment to some molecules. We took an example of one molecule and said how based on the number of carbons we observed and coupling with fluorine, we could even get the structure of the molecule approximately. That was easy. Can we extend it further, the depth? I will give another one important application of depth, how we can utilize depth to get the structure of the molecules. Here I am taking example of 2 monoterpenes, identifying the correct structure of monoterpenes. That is our challenge. Let us see what we do. The challenge is I have to use the depth experiment to identify the correct structure of which of these things. There are about 6 molecules, all are monoterpenes. We want to find out what is the correct structure of it by using depth experiment. And a depth experiment was done for this thing. Now, if you do the depth experiment, this is a conventional carbon-13 experiment. This is depth 90, depth 135. Already I told you depth 90 gives you only CH positive. and depth 135 shows you CH and CH3s are positive, CH2s are negative. Just look at it, and then leftover peaks is from the quaternary, from the conventional NMR spectrum. We can easily identify. Look at it, there are 3 CH3s which are positive. I am sorry, 2 CH3s which are CH3 has 2 peaks which are positive here, and CH2, if you look at it, 1, 2, 3, 4 CH2s, because of negative intensity in the depth 135, I know these are CH2s. And if you look at the CHS, we have 1, 2 and 3 CH peaks, and from the conventional carbon 13 spectrum, there is only one peak which is left here, that is a quaternary carbon. I know quaternary carbon is 1, there are 2 CHS, 2 CH3s and 4 CH2s and 3 CHS. This is what the conclusion I draw from the depth experiment. Now our job is to identify which of these terpene is the depth spectrum corresponding which of these terpenes. If I know that, I can get the correct structure. Using this information, we will go further. Okay. Now if you go further, our job is to identify in the molecule 2 CH peaks, CH3 peaks and 4 CH3 peaks, all these things we have to identify. Look at the molecule 1 here. Here you have 3 CH2s. See what is highlighted here, but what we require is 4 CH2. So that is not the structure. Look at this one, again 3 CH3s, that is not our structure. Go to the next one, 3 CH2s, that is also not our structure, because here we needed 2 CH3, here we needed 4 CH2s. Come back to this one, 3 CH3s, that is also not our structure, because experiment shows only 2, depth experiment. Come to this, again 3 CH3s, ruled out, that is not our structure. And come to this, you have 2 CH3s, 4 CH2s, 3 CHS and 1 quaternary. Perfect. That means from the depth experiment, I can conclusively say this is the structure of the monoterpene. This is what the depth experiment has been done on this molecule. Go further, another experiment has been done, depth experiment, where you can see here 2 CH3 peaks you can see, and 3 CH2 peaks, 3 CH peaks and 2 quaternary peaks here and here. From normal carbon 13 spectrum, we see 2 quaternary peaks and 2 CH3 peaks, 3 CH2 and 3 CH peaks. This is what we observed from the depth experiment, depth 90 and depth 135 and combination of normal carbon 13 NMR. What is the possible structure now? We will try to analyze this one. Of course, there are 4 CH2s, that is ruled out, because according to that we need to get only 3 CH2s, so that is ruled out. What about this? This is 4 CH2, that is also ruled out. This one 3 CH3, that is ruled out because we wanted only 2 CH3s, that is also. Look at this one, this is 3 CH3, that is ruled out, this is also ruled out, and finally what is left with this molecule is 2 CH3, 3 CH2, 3 CHS and 2 quaternary, and that must be the structure of the molecule. So using the depth experiment from the carbon 13, very easily we can even make the assignment and get the correct structure of small molecules like this. So I showed you 2 examples of terpenes, very interesting example taken from the book of Niels. So it's a very good example. Okay. I think with this I have covered quite a bit about carbon 13 NMR. About 2 or 3, 4 classes we discussed at stretch, and I showed several examples, several applications of carbon 13 NMR, depth experiment, problems we encounter in the experiment if we are mistuning 90° or J coupling is not correct, and how we can utilize depth experimental information to get the correct structure of small molecules like this. So with this fairly large enough information I have given you on carbon 13, we will continue further with the analysis of the spectrum of different heteronuclei. I took extensively long time for carbon 13 because it is another extensively used nuclei apart from proton. Other heteronucleic some other than these two are used in some inorganic chemistry, material chemistry, etc., but not extensively used like proton and carbon. Nevertheless, we can analyze lot of such heteronuclei experiment, heteronuclei NMR spectra and get something some information from these things. Okay. We will start with analysis of 1D spectra of selected heteronuclei. We start with the fluorine NMR. Of course, fluorine is a 100% abundant nuclei, spin half nuclei, very friendly nuclei like proton. Spin half nuclei are always friendly nuclei, very easy to read and easily understandable. Further, it has 100% abundance. So, experimental spectrum we can obtain very fast without much difficulty. This is the fluorine 19 NMR spectrum of this molecule C6H3F3H2Br. Now, we have to make the assignment of fluorine. How do you make the assignment of fluorine? I would clearly say this is the fluorine 1 and this is fluorine 2. Why? Remember, I explained to you about the multiplicity pattern you get in the phenyl protons. Well, now, if you look at this fluorine and this fluorine, there is a chemical equivalence, but this couples with this fluorine equally, because the one ortho coupling of this fluorine to this fluorine and this fluorine to this fluorine is identical. It gives rise to a triplet like pattern, doublet of doublet, two central lines overlapped, it is going to be a triplet. At the same time, we also have the coupling because of two remaining protons here, that is also chemically equivalent. These two protons are also chemically equivalent, they will split this fluorine equally, then it is going to be triplet of triplet. Again, each line of the triplet is a further split into triplet because of protons. So, proton fluorine coupling. So, this fluorine experiences proton fluorine fluorine coupling and also fluorine proton coupling. Coming to this fluorine 2, interestingly they are chemically equivalent. It can split with one of this fluorine, become a doublet. Similarly, it can split with another proton and it can become a doublet. So, this fluorine 2 has to be doublet of a doublet. Exactly, look at this. So, I can make assignment, this is fluorine 1 and this is fluorine 2. To confirm further, we can do one more thing. We can decouple protons, observe fluorine. What will happen? All FH couplings are removed, only FF couplings are retained. And when we do that, this is the proton coupled and this is proton decoupled. When you decouple proton, all FH couplings are removed, these are only FF couplings removed, retained. FH couplings removed and FF couplings are retained here. So, very simply you can see this multiplicity triplet is because of this fluorine, this coupling to these two equally and these two fluorines become a doublet. So, very easily you can identify, and I showed you the advantage of decoupling of the heteronuclei when you are seeing such type of spectra. If there is a complexity, you can do selective decoupling or broadband decoupling of the heteronuclei. What happens if there is a coupling to other nuclei? Boron. The boron has two isotopes, spin 3 and spin 3/2, and abundance is approximately 20-80. Boron 10 is 20, boron 11 is 80. Boron 11 is 3/2, boron 10 is spin 3/2. When it coupled to spin off nuclei, what will happen? Boron 10, when it coupled to spin off nuclei, let us say one nuclei spin half, 2 into half plus 1, it is going to be 2 into 2, 4. Of course, spin of the boron 10 is 3, 4 into 3 is n. Of course, we have only one spin, one boron we are taking into account. 2 into 1 into 3 plus 1, it is going to be 7 lines. Go to boron 11, 2 into n is 1, I is equal to 3/2, 3/2 into 2 it will go and it will become 3 plus 1 4. So, if any of the spin off nuclei like fluorine is coupled to boron 11, it gives 4 lines. If it is coupled to boron 10, it should give 7 lines of equal intensities. 7 lines are of equal intensity and 4 lines are of equal intensity. But the intensity ratio between these will be 1:4 because abundance is 80 and 20. If both the boron isotopes are present, then what will happen? You have coupling because of both boron 10 and boron 11. One gives you 4 lines, other gives you 7 lines. See, this is exactly what happens. This is NaBF4 molecule in D2O. Now, boron spin 3/2, it is going to give 4 lines, abundance is 80%, boron spin is 3, it gives 7 line pattern. Intensity ratio is 1:4. And the separation of this gives you boron 10, boron 11 fluorine coupling, this is boron 10 fluorine coupling you are going to get. Okay? And this coupling is quite large compared to this one. Very easily you can analyze coupling of quadrupolar nuclei to fluorine. and this is a information you will get. Center of this to center of this gives you what is called isotopic shift. When the boron is isotope is changed from 10 to 11, see this is the shift you are going to see. Always I told you yesterday also, with the heavy isotope always shift the chemical shift to the higher field. Another molecule fluorine NMR, again boron coupling. Here it is a potassium bromine CF3 4 times. Now we are looking at the fluorine, so it does not matter. What we have to worry about is coupling with boron. Now boron, when it, as I said, there are two isotopes. Boron spin 3/2 gives 4 lines very of equal intensity, and then boron 10 couples to fluorine gives 7 lines of equal intensity. So intensity ratio is 1:4 between this and this, and this separation gives you boron 11 a fluorine coupling, and say adjacent separation of any of these two peaks gives you boron 10 and fluorine coupling. Very easily you can do that. Of course, we can also have a bromine. There it is boron, now it is bromine. Bromine has two isotopes, 79 and 81, and interestingly both of them are almost of nearly equal abundance, 49.5 and 50.5 like that, and both are spin 3/2 nuclei. Now in this case what will happen? You will get 4 lines of equal intensity, and both of them will give 4 lines, both bromine 11 and bromine 79 will split fluorine into 4 lines of equal intensity, and equal not only equal intensity among them, also between boron bromine 18 and bromine 79 couplings. So this is what is happening, and now we are going to see 4 lines here, strong 4 lines. This is 1J coupling of bromine 81 fluorine. This is 1J coupling of bromine 79 with fluorine. Small change in the coupling is there, 1695 and 1570, about 100 Hz difference is there, and usually this this type of broadening is not observed. It is very broad because of bromine. So it appears as if we are not resolving peaks here, but there are peaks which is not completely resolved. Okay. So you can get all the coupling information very easily. Go further. Now let us look at the fluorine spectrum of a molecule like this. And this has two possible, this conformation could be like this. When the conformation is like this, there are two fluorines. Interestingly, we have a fluorine-fluorine coupling here. That is quite large. Fluorine-fluorine coupling is quite large, and it gives us a doublet. And there are two fluorines which are two different chemical shift. This is F1 and F2, and each of them will be a doublet because of large separation is because of FF coupling. Okay. This fluorine split this into a doublet first. This also splits into a doublet. Further, if you go to the fluorine 1 experiences 3 different types of couplings. One is FF coupling, other is this fluorine 1 can couple to this proton and also to other proton. So it experiences 2 different couplings. Both are single protons. As a consequence, this is going to be one doublet because of fluorine and other doublet of doublet because of 2 other protons, which is 3 bond coupling. 3JFH couplings are there. 2 3JFH couplings of almost nearly equal strength. Small difference is there. Okay. So as a consequence, large doublet is because of FF coupling and doublet of doublet is because of 2 FH couplings, which is slightly differing in the strengths. Let us come to this one. This fluorine 2 is very interesting. This has a large coupling because of fluorine doublet, but each of them has 2 couplings because of 3JFH. Here like here, 3 bond proton fluorine couplings are there, 2 of them. So each of them will split into a doublet. So it is like here, doublet of doublet. Further, interestingly, this fluorine also coupled to the CA3, 5 bond coupling is there, and that 5 bond coupling because of CH3, 3 chemically equivalent protons, each line of this doublet of doublet is going to be a quartet. So what is the pattern you get for this fluorine 2? The pattern what you are going to get, first it will split into a doublet, and each line of the doublet is split into doublet of doublets because of 2 3JFH couplings, and each line of this 4 line pattern, doublet of doublets, and also this 4 line pattern will be a quartet because of 5 bond coupling between Ca3 protons and fluorine. So, it is going to be what the pattern you are going to get. Largest coupling is doublet, doublet of doublet of doublet of quadrates. So, this is doublet of doublet of doublet DDD pattern. Here this is DDDQ, and this is what the pattern is. Of course, when you are looking for the fluorine NMR, also you can get the satellites. Like carbon, when I observe proton, I saw carbon 13 satellites. Now, fluorine is also 100% abundant spin of any other dilute spins coupled to it will be a satellite. Exactly, if I take the molecule like this fluorine NMR gives a single peak, but this mercury couples to this fluorine equally because there is a symmetry. As a consequence, you see on either side of this 2 peaks. These are the expanded version here you can see, and interestingly this mercury abundance is about approximately 16% or so. As a consequence, very strong intensity satellites you are going to see. The intensity of the satellites can give you a rough idea about the abundance. This compared to carbon 13 is quite large, and we know this abundance of mercury is about 16%. That is what it is, and we can get even the satellite spectrum, and this separation if you measure, you will get mercury fluorine couplings. You understand? The satellite spectrum you can get for fluorine similar to proton, where dilute spins give rise to satellites, and measuring this separation gives you J coupling between fluorine and the dilute spin. Okay. With this, we will go to another interesting topic called isotopic effect. This you must remember, because whenever you do fluorine NMR, be careful. Fluorine is a very interesting nuclei. This is its chemical shift is very sensitive to isotope effects. Replace the one of the for example proton by deuterium effect is seen. We already saw that. Where similar to that, in the case of fluorine chemical shift, isotopic effects will be dominant. We will see an example like this. Whenever you have to analyze the fluorine spectrum, you have to be extremely careful. Look at this carbon 13 labeled dibromofluoromethane. There are 3, this is carbon 13 labeled here. So, there are 3 abundant spins, proton and fluorine, and carbon 13 is labeled. So, it is also abundant 100% we can say. So, these are all 3 heteronuclei weakly coupled AMX spin system it forms, done. Okay. And this is the proton spectrum. If I analyze this, I will get JCH and JFH, and the CF is a passive coupling. All those things we have discussed, and here also fluorine spectrum, JCH we do not get, other 2 couplings we get. If you go to 13C spectrum, we get JCH and JCF, JHF we do not get, that is a passive coupling. This we have been discussing quite a bit. That is also not an interesting thing. What is interesting thing is the expansion of one of the peaks here. Any one of these peaks we have expanded for all the 3. And it is a very good spectrum, very good line width. If you carefully see, proton has a very sharp line, single line, and line width is 0.3 hertz. Similarly for carbon, whereas look at this fluorine, it appears like a triplet. Where is this triplet coming from? Why fluorine peak is a triplet? But it is a genuine peak. There is no other protons or anything for it to couple to give a triplet. Usually we say if it is coupled to CH2, some other CH2 or CF2 group, we can say it is a triplet. But there is no such thing here. Then why fluorine 19 peak is a triplet? We will understand that. For that, we have to go into what is called isotope effects. Bromine and 79 both have spin 3/2. Both have the natural abundance of 40 equally 49.5, 50, I will say 50-50. Both of them of equal abundance, both are spin 3/2. That is what I told you when I analyzed the bromine coupling to fluorine in the previous example. Let us see what are the isotopomers present in this molecule. One thing is both the bromine could be 79. There are 2 isotopes, equal abundance. There is a possibility both bromine could be 79. That is fine. There is another possibility, this could be 81 and this could be, both could be 81. That is also possible. Another possibility, this is 79, this is 81. One more possibility, this is 81, this is 79. But what is the difference between this and this? You can't make out. So, C and D are equally probable. If I say there are 100 molecules, 25% of 25 molecules be both bromine 79, 25 molecules will be both bromine 81, 25 molecules with one bromine 79 and this bromine 81, 25 molecules will have this bromine 81 and this bromine 79. As I said, C and D are indistinguishable, they are overlap. So, what happens? You get 3 peaks. In reality, there are 4 molecules, 4 spectra, but this spectrum of these 2 molecules are indistinguishable, they overlap. As a consequence, you get 1 peak for this, 1 peak for this, 2 peaks overlapped will be a triplet like pattern. So, 1, 2 and 1 intensity ratio you get. Actually, there are 4 peaks from 4 different isotopomers and the peak positions have changed here because of what? The isotopic substitution. That is the important point. You understood? Now we can understand why we got a triplet for fluorine. You may ask me a question, why not for proton and carbon similar effect? Fluorine is more sensitive for this, not for other 2 nuclei. Alright. We will take another example of CFCl3 where we can see the isotopic effect dominant here. Again fluorine CFCl3, if I take the spectrum, how many peaks we expect? Take CHCl3 chloroform. If you take proton NMR, how many peaks we get? There is only one proton. I told you single nucleus gives only 1 peak, no other coupling. Forget about carbon 13 here, dilute spin coupling. Abundant spin proton we get only 1 peak. C12 proton, C12 attached to proton we will get only single peak. Similarly, CF33 also should be single peak because this is also similar to proton, 100% abundant with spin off. So, fluorine NMR of CFCl3 also should give a single peak, fair enough to assume, and it is true, it has to be a single peak. But interestingly, you get 4 peaks here, 1 peak here, 1 peak here, 1 peak here and 1 peak here. This intensity is 100%, one is 95, 30 and 3. True spectrum, real spectrum. How do we get these 4 peaks? Why not a single peak like CHCl3? This is where isotopic effect comes into the picture. Forget about carbon 13 is natural abundance. So, interpretation we can do like this. Before that, you should remember chlorine 35, there are 2 isotopes chlorine. One is 76%, chlorine 37 is 24%. Like bromine we got 79, 81, 50, 50. Here also we should consider the abundance. One is 35, other is 24, 76 and 24. There are various isotopomers we can think of. What is the possibility 1? Possibility 1 is all the chlorine could be 35, possible. So, 76% abundance, 76, 76, 76, all 3 are present. Then if you take the population of this, it is 4.438, multiply 0.76, 0.438. I will say this is 100% intensity peak. Make it as 100%, normalize it for 100% intensity. So, if I take a molecule, if all the 3 chlorine are 35 in this molecule CFCl3, then I get a 1 peak, I call this intensity 100. Alright. What is the possibility 2? Possibility 2, these 2 chlorine could be 35, this is 37. Again 3 such possibility, these 2 35, this is 37 and this 2 35 and this is 37. There are 3 such possibilities. Okay. Now, what is the population of each isotopomer? One is 0.76 and this is 0.76, these 2 and this is 0.24. We told you, I already told you chlorine 35 is 76% abundance, chlorine 37 is 24%. So, for each of these molecule, what is the population? 0.76, 0.76 and 0.24. So, this is 0.138. But that is not all. There are 3 such possibilities. Like we saw in the other example bromine, there are 2 such possibilities, they added the intensity added up. So, there are 3 such possibilities. So, it gets multiplied intensity. So, 0.138 into 3 you get 0.415. If this is 0.415, what is this intensity compared to the previous peak? Previous peak I took it at 100%. Normalized with respect to that. This turns out to be 95%. Fair enough. You could assign the second peak. Now what is the another possibility? 2 chlorines are 37, one is 35. There are again 3 such possibilities. These two can be 37, this is 35. These two 37, this is 35. And these two 37, this is 35. 3 possibilities are there. Now what is the population? Only one is 135 is there, 237 is there. So multiply as 0.76, 76% for 35, 24% for these two, it is 0.044. Again 3 such possibilities, 0.132. Normalize that with the first one, it turns out to be 30%. Very interesting. So we got the third peak also of 30% intensity. What is the last possibility? All the chlorine are 37. Calculate the population. There is only one such possibility, 0.0134. And normalize it with the other one, first one, it is 3%. So what is the intensity ratio you get? 100, 95, 30 and 4. So there are 4 peaks coming because of different isotopomers. So the intensity of the peak is due to the statistical distribution of isotopomers. Remember, intensity of the peak is due to statistical distribution of isotopomers. Isotope shifts are expressed always in ppb, and this is what you are going to see. Very dominant effect, isotope effect on fluorine. So I took the example of 2 examples, and then this is the another example, CFCl is another example where I showed population statistical distribution give rise to this. So this is the time is getting up. I am going to stop here, but I want to summarize what we discussed today. We continued with carbon 13 yesterday, and then I showed you using depth. I can use the knowledge of depth, find out the number of CH3 carbons, CH2 carbons, CH carbons and quaternary carbons, and use this knowledge to identify certain structure of small molecules. I showed with the example of terpenes, 5 or 6 different monoterpenes were there, which we do not know. But I took the advantage of depth experiment, identify number of CH3 is present, number of CH2 is present, CH is present and quaternary carbon, and find out which molecule matches with that, and we could identify that. Then continuing further, we started analyzing the spectra of many other heteronuclei. Next we took fluorine. Fluorine is again a spin-off nuclei, 100% abundant. I took several examples of the fluorine. Fairly easily we could assign fluorine coupling, fluorine proton coupling, and multiplicity pattern how we get when there are different heteronuclei present, fluorine coupling, fluorine proton coupling, everything we analyze that. And interestingly I also pointed out one more thing, satellite pattern, satellite peak also we see in fluorine NMR. I took the example of CF3HE, that molecule CF3HE, and we could see fluorine NMR coupled to mercury, we get mercury coupling as satellites. That also we understood. Most important point you should remember is fluorine is very sensitive to isotopic substitution. We took 2 examples and showed how different isotopomers can give rise to different peaks, and there is a shift in the positions. It is very confusing. See, simple example of CFCl3 should give you a single peak, but it gives you 4 peaks of different intensity, 100, 95, 30 and 3, and we could identify each of them and explain the intensity pattern based on the population of the isotopomers. The intensity comes because of the statistical distribution of different isotopomers, population of different isotopomers. So this is what we understood. I have stopped here. We will come back and continue the analysis of fluorine and other heteronuclei in the next class. Thank you very much.